Hello everyone. Now let us move to the next part, that is introduction to waves in quantum mechanics. So let us know the introduction part at first. So what is the fundamental difference in between classical mechanics and quantum mechanics? So for classical mechanics, future prospects of particle is known if one knows initial position and momentum. And it are these all theories of classical mechanics are applicable to macro objects. But in quantum mechanics, future prospects is known, but in probabilistic manner. They are not exactly known. That means you cannot have a sure shot knowledge. And it applies to micro realm, like at atomic level, subatomic level. So every observation in quantum mechanics is based on probability. And this probability is described as a wave function of the given particle. This probability is described as wave function of the given particle. So now let us know what is wave function. It is denoted by psi, and remember that psi has no physical interpretation, like you cannot know what it is physically saying. The only information which one may get is that when you take the complex, the product with its complex conjugate, like if psi is a plus iota b, then its complex conjugate is a minus iota b, and when you multiply them, you get psi square, magnitude of psi square, that is a square plus b square. And that provides us the required recipe to calculate the probability associated or the expectation values associated. And these are part of our syllabus. Okay. So this from this we could derive probability. Okay. For example, probability of particle with wave function psi in between two positions, say x1 and x2 on x-axis would be given by this formula, that is you integrate the magnitude of psi square with respect to dx in between the limits x1 and x2. So in that way, whatever the values come, that is the probability of that particle being found in between x1 and x2. Now think, as the particle exists somewhere, hence its probability of being found anywhere in the space must be 100%. Suppose that if I say the probability of particle being found in between x1 and x2 is something which is, suppose that for example we may say that it is 0.3, then the probability of particle being found in all the space, that is in between minus infinity and plus infinity, should be overall 1, because at some place that particle should be there, it must exist. So mathematically, when you change the limits from minus infinity to plus infinity in all the volume, that is dv means volume, you must get the probability 1. Okay, so we got the probability 1 in that way. We call this mathematical condition as normalization. So every wave function must be normalized. That means every wave function, the particle which is associated with that wave function should exist somewhere in the whole universe. Now, as a wave function is here, that as wave function exists, hence it must have some character. Okay, and we call them well-behaved wave function. And properties of well-behaved wave function is very simple, that phi must be continuous and single valued everywhere, and its partial derivative with respect to x, with respect to y, and with respect to z should also be continuous and single valued everywhere. Third part, that psi must be normalizable. That means when you find its integration, or say probability in all the space, and this is going to be b, in all the space you should get 1. So this is what we call normalizable. And it also means that on infinity psi must go to 0, so that this value over all the space becomes a finite quantity, because on infinity if psi is not zero, then this is not going to be 1. This is not going to be finite quantity. That is the mathematical restriction. So in a model situation of theory, these conditions are not always obeyed. Still, we would regard this to be true in all theoretical cases. Because we are studying theory right now, so we should regard this as true. Now, let us know the wave equation. Recalling wave equation, that is double derivative of y with respect to x, and it is partial derivative, it is 1 upon b square, and double partial derivative of y with respect to t, and this v is nothing but speed. So y is displacement on a string, or it could be pressure of the sound wave, or it could be electric or magnetic field's magnitude. And this is the way it is traveling in x direction, and t is obviously the time, v is the speed of the uh, traveling of the wave. And this whole equation could be derived from the second law of motion for mechanical wave, or from the Maxwell's equation of the electromagnetic wave. You will read it in those part as well. Like you will get the same equation in mechanics and in the electrodynamics. Now let us know the very important equation, which is Schrodinger equation, which will actually talk about this wave equation. Okay. So from the electrodynamics, because electrodynamics also talks about EM waves, and so we could get the information of wave. Wave could be described as psi, that is A e exponential minus omega in bracket t minus x by v. Okay, and when you multiply omega inside, it gives minus iota, bracket opens, and inside the bracket omega t minus kx. And as omega by v is k, so omega times omega divided by v becomes k here, and k is nothing but propagation vector. Now, what you could do, you could also write it as by taking the 2 pi out of the omega, because you know that omega is basically 2 pi by t, and it could be written as 2 pi nu, that is frequency, because frequency is 1 by t. So this is omega. So when you take out 2 pi from here, here only frequency is being left, and here only 1 upon lambda is being left, because you know 2 pi by lambda is nothing but propagation vector k. So you should know that, and here 2 pi nu is omega. So hence finally we could have this equation that a exponential minus iota by h bar, bracket close, then bracket opens again, and inside the bracket et minus px. We know E and P directly, so we have converted it into this format, and this is wave equation of free particle. Now when we find the double derivative of this psi with respect to x, just to double differentiate this equation with respect to x, you will get that double differentiation, that is partial differentiation of psi with respect to x is minus p square divided by h bar square psi. So when you do the basic thing, you get that p square psi is minus h bar square double derivative of psi with respect to x square in the partial fashion. And now let us find the single derivative of psi with respect to time. In this way you get single derivative of psi with respect to time is minus iota e by h bar multiplied by psi. And in this way e times psi is equal to iota h bar partial derivative of psi with respect to t. And here we did nothing, this was this value, so minus h bar by iota is nothing but iota h bar, because we know this minus is minus 1 actually, and minus 1 is iota multiplied by iota. So when you cancel it out, it comes out iota h bar. So this is our important finding. Okay. So using this equation 3 and equation 4, we could write energy equation, because energy is nothing but kinetic energy added to the potential energy. So kinetic energy is Pa square upon 2m, and we know the value of Pa square from here. Okay, so when we put that and we multiply psi everywhere, here, here, and here, so you get it that it is iota h bar, uh, partial derivative of psi with respect to t minus h bar square divided by 2m, then partial derivative of psi with respect to x plus potential multiplied by psi. And this same equation is very important equation, which we call time dependent Schrodinger wave equation in one dimension. Okay, and in three dimension you just need to expand this to the x, y, and z, all three, like this. So finally in three dimension it is going to be like this. Okay. So one must remember that we call it in that format, it is iota h bar d psi by dt equal to minus h bar upon h bar square upon 2m plus potential multiplied by psi. That is wave function. And now this is time dependent function because we have the timed equation here. We have some quantity which involves time. Now suppose that we want to know what is time independent form, or we also call it steady state form. So let us again recall the wave function from here. We have this very important wave function. Okay. And what we need to do, we need to separate time and everything else. So when we separate, just by rewriting it, not doing anything extra, we are just rewriting the wave equation as this. We separated the multiplied terms and it got a exponential minus iota divided by h bar, bracket closes, time, into exponential iota p h bar by x. Okay, we are just separating here time in position terms. So when you get, we call this positions function by the slant psi, in psi in italics. This is the normal psi, this is the slant psi. Just know this slight thing, and this is the times function. Now what we do, we substitute this value of psi into the time dependent form. The idea is very simple. Separate it and substitute the psi into the time dependent form of Schrodinger's wave equation to get time dependent form. So when we do that, we get simply time dependent form. This is just a basic mathematical calculation which you can do it at your own. This is double derivative of psi with respect to x, y, and z plus 2m upon h divided by h square multiplied by e minus u by psi into psi is equal to theta. And I am just correcting it at some point whenever in notes there is something missing, I will keep rewriting it. So this equation is very important and we are going to use it often. Now let us understand very important aspect of wave, that is linearity and superposition. So suppose psi is linear, that means the wave function has terms which involve psi or derivatives of psi, but no terms are independent of psi or that involve the higher power of psi. In that case, you could say that psi is linear. Okay, that psi could be there, derivative of psi could be there, but functions which are independent of psi or functions which have higher power of psi should not be there. And as a result, a linear combination of different solution of Schrodinger wave equation will be also another solution. For example, if psi1 and psi2 are solutions of this Schrodinger wave equation, then a1 multiplied by psi1 plus a2 multiplied by psi2, which gives the another uh, wave equation, wave function psi, is also going to be a solution. And wave functions do simple superimpose. That means mm, you could add them simply. Suppose that you have two wave function at the same time, psi1 and psi2, then you could simply add them to get the another, that is psi, or you may say psi3. Now let us understand about the expectation value. We already know the probability. That probability is being found as from x1 to x2. This is probability, and this value is nothing but the multiplication of complex conjugate and the normal wave function. Now, expectation value helps us to get information about the particle from wave function. For any quantity, expectation value will be denoted by using left or right caret. Okay, like this. So expectation value of, suppose that there is a operator gx, so or quantity gx, so you need to find the expectation value. So it would be found like this. Okay, and we will understand this while when we will solve the questions. But right now, just know that this is the operator, and operators are something which perform a specific mathematical actions or acts. For example, addition or multiplication is also a kind of operator, because you are kind of doing some operation. If there is plus sign, you are adding them. If there is multiplication sign, you are multiplying them. That means you are doing some kind of operation, and that is why they are named operator. So what you do, you just integrate from minus infinity to plus infinity the complex conjugate, and then the normal wave function, and in between them there should be the operator. So what that this means that this is the complex conjugate, and after this there is operator, and this is the normal wave function. So you need to operate this operator on this wave function to get something. This will result in some kind of function. Suppose that fx. So now this function fx and this function is going to be integrated from minus infinity to plus infinity with respect to x to get the desired expectation value. Now let us know about operators. Free particle wave function is given by this value. Okay, and when you differentiate that partially with respect to x, you simply get iota divided by h bar p psi, and from here you separate out p psi to get h bar by iota, and differentiation of psi with respect to x, and from here you could just simply find that it is going to be p is going to be minus iota h bar, and the partial derivative operator with respect to x, and we have removed psi from both the sides to just get what is operator for momentum. Like suppose that if you need to find the momentum, you just apply this mathematics to any kind of wave function and you will directly get the momentum. So this is what we call a momentum operator. It says to find the partial derivative and then multiply the result by minus iota h bar to get the momentum. Similarly, for energy, you may do it by iota h bar dy dt, and cap indicates that it is operator, that you need to do the some operations. This is nothing but some operation, like you just need to find the partial derivative of anything whatever comes after that. Okay, suppose that it is like iota h bar d by dt, and after this it comes psi. So you need to find this value, then multiply the result with iota h bar to get the energy there. So in the plain and simple language, if it is written by E cap psi, then you must find this value, that is iota h bar d by dt psi. Hence, operators are nothing but mathematical instructions we need to perform with the associated function. And if you have the momentum operator, you can easily get to know the kinetic energy operator by using the formula kinetic energy is equal to momentum s square by 2m. We did that, we got this, and kinetic energy's operator is minus h bar s square by 2m and the double differentiation with respect to x in the partial fashion. Now let us again relate the operator and expectation value. So operator expectation value of momentum would be given by the formula which we have just studied here. Okay, that there should be the first complex conjugate of a function, then operator, and then the operator should be operated on psi. So there are mainly two functions here, first and second. When you do that, you simply get this, and these are nothing but class 12 level integration or differentiation. Now let us understand by eigenfunction and eigenvalue. Suppose we need to operate this operator on psi, and then we get something which is some constant which is multiplied by psi. If the answer is always in the same fashion, we call psi to be eigenfunction and an to be eigenvalue. Suppose that we have an operator of this nature that it says you to find the double differentiation with respect to x, and suppose that we have psi that is exponential minus 2x. So we need to find this now. So when we are operating this g on psi, that means we are trying to find the double differentiation. So this is our expression, and when you double differentiate this exponential minus 2x, you will get 4 exponential 2x. And again, when you check, this exponential 2x was nothing but again psi. So this is the format we got here, that g operator over psi is 4 times psi. So this is our same formula which we just got here. G operator is some constant 4 times psi. So an is 4 here. So we got to know, okay, this 4 is nothing but eigenvalue and this psi is nothing but eigenfunction. This is pretty simple. So some quantities and operator which we should remember. For position, it is plainly just position. Okay. For momentum, we just got to know that it is h bar by I d by dx. Okay. Or in 3D, we could just write minus iota h bar psi. This minus I is just we know that iota and minus 1 by iota is same. Okay. How? So this minus iota could be written as iota times iota, iota square, and this is 1 by iota, so you cancel it, so LHS becomes RHS. For the potential energy, it is again the same. For the kinetic energy, we just found it that it is h bar square by 2m ds partial derivative, double derivative with the minus sign. Now total energy is nothing but iota h bar d by dt, and total energy, that is in Hamiltonian form, is kinetic energy plus potential energy. So we are done with the wave aspects, and we have studied something very significant today. Okay, for example, this eigenfunction and eigenvalue, they will have this concept is very important. Okay, you need to expand this concept whenever required in the future also, for example in atomic and molecular physics also. And these all things like finding the expectation value, there are many PYQ which we need to solve, and there is one assignment for you. If you need to solve these questions for the better sound understanding, although there is very limited number of PYQ except the expectation value part, so you need to follow two books. The first book is Concept of Modern Physics, and the second one is by N. Jatili. There are a lot of solved problems there. Just go and solve them. You will get it, specifically the second book. So now let us meet in the second next part of this.